So, the actual definition of a quantum number, or what they're used for, quantum numbers are used to describe the distribution of electrons in atoms. Think about giving an electron an address. It's really just a way that we can use to locate where an electron is, kind of in an abbreviated form. Now, in actuality, they're very complex, and this isn't even 100% accurate. But it's kind of a cool way for us to think about identifying where an electron is or might be. So there are four quantum numbers, or four ways we identify an electron. The first number we use, we're going to say, is N. And this is really just our principal energy number. So N will tell us our principal energy level number. The second one is a cursive L, or a lowercase l. It's our angular momentum quantum number. Really, we just need to know it's the second number in our address. Then we have M. It's going to tell us the magnetic quantum number. Really, we just need to know it's our third number in our address. And then we have S. And S is going to tell us the spin of our electron, or the electron spin quantum number. It's going to be the fourth number we see in our address. So the principal quantum number can be anything that is a principal energy level. So it could be N 1, 2, 3, 4, 5, 6, all the way up to 7. And it is described as the average distance of electrons an electron is to the nucleus. So it gives you a general idea of how far away it is from the nucleus. The larger the value, the further from the nucleus that electron is. Really, this is just our principal energy level number. So we're always going to fill our principal energy levels in a certain way. And there are three principles or ways that we fill electrons and where those electrons go. The first principle we have to know in order to properly identify an electron is something called Aufbau's principle. An Aufbau's principle really just tells us each electron will occupy the lowest energy orbital available. So it's going to fill from the least amount of energy to the most amount of energy. And oftentimes we'll see diagrams that look like this. In fact, this is what we're going to use to figure out our quantum number of an electron. And when we go through this, here is our lowest energy, up here is our highest, and we'll notice we would go 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5D, 6P, and so forth. And when you look at this, you'll notice that it is the same as those little arrow charts that we use to write electron configurations. So really, the reason we're adding electrons in that particular order is because of the Aufbau principle. We're always going to fill from the lowest energy level up to the highest with electrons that we have. So when we go to figure out our principal energy number for our quantum numbers, we're going to have a diagram that looks like this, and we're going to fill it first in our increasing energy. So N can be any number between 1 and 7, because when we look at our periodic table, those are actually eventually going to be our period numbers, and there are only 7, so you can't have a principal energy number or an N of anything greater than 7 because it doesn't exist yet. But we'll always see our N as our principal energy level, and it'll typically be shown on our y-axis. Then we have our angular momentum, or a quantum number, which is an L. And really it tells us the shape of the orbitals or the sublevels, but what we can think of it kind of is S, P, D, or F. So 0 will be an S orbital. 1 will represent a p orbital, 2 will represent a d orbital, and 3 would represent an f orbital. So when we look at the same chart, we might get our first number would be a number n, 1 to 7. Our second number then is going to be a number between 0 and 3. So any s orbital would be L equals Z. Any p orbital is going to be L equals 1, and you can see them as you go up. Any d orbital is going to be L equals 2, and any f orbital would be L equals 3. So you might see a number that would go 1, 0. That would mean you're in the first principal energy level and you are in an s orbital. Or you might see a number that goes 2, 1, and that would mean you're in the second principal energy level, but because the next number is 1, you are now in the p orbitals. So that was our n and our l. Those are our first two numbers. We also need to know that when we fill electrons, we follow something called Hund's rule. Hund's rule tells us that one electron enters each orbital first and then fills with a second. So let's pretend these are my p orbitals. So there's 1p orbital, 2p orbitals, 3p orbitals, and they can each hold 2 electrons. That's why I have 3 of them. And that's how I know they're p orbitals. Okay, so the first electron I would add, we're going to add it as an arrow, just for sake of what's going to come next. And I might add that arrow up. Now, what Hund's rule tells me is that I'm not going to double up an electron here. First, I'm going to spread out all my electrons as best I can. And if you think about that, electrons are negative, and negatives do not want to be together. So I'm going to go negative, negative, spread it out. If I have my third electron, I'm not going to double it up. I'm going to put it in a different suborbital if it's available. Now, when I have my fourth electron, I have to double it up, and I'm going to put that arrow facing the opposite way. My fifth one, I have to double up, and my sixth one, I have to double up as well, because there's no other space for them. It doesn't actually matter which one you double up first, as long as you have spread them all out first. However, I am going to suggest that you follow the same pattern over and over and over again. And that leads us to our m quantum number. It's going to tell us the orientation in the orbital or the 3D space. And it can be anything from -1 to 0 to +1. And we think about it kind of like a number line. 0 is going to be our middle. Then we can have negative numbers and we can have positive numbers. Okay, so we're going to go back to our same orbital or off-bond diagram. We'd have our principal energy number, that would come first. We'd have our angular momentum, our L number, that would come second. And now we have our M number. And our M number refers to which orbital we are in. Okay, the middle one is always 0. 1 to the left would be -1, 1 to the right would be 1. It's important to note if you only have s orbitals, you're only going to have the 0. But you can look at up here our d orbitals, and we have 0, 1, 2 to the right, and 0, -1, -2 to the left. And our f's, because they hold more electrons, are going to go all the way to -3 and +3. So you could have a quantum number that went 2, 1, 1, +1, and that would mean you had an electron right here in this orbital. If it was 2, 1, 0, it would mean your electron was in this middle orbital. And if it was 2, 1, 2, 1, -1, that would mean your electron was here. Okay, the last thing we have to worry about is something called our spin. We say electrons can either have a positive spin or a negative spin. And the Pauli exclusion principle tells us that 2 electrons actually can occupy an orbital, but they have to have opposite spins, okay, right? So we fill electrons from the lowest level to the highest level. Then we saw that we spread them out as much as we can in Hund's rule. And now we're going to have Pauli exclusion principle that tells us they can be in the same orbital, but they have to have an upspin or a downspin. And we label that as +1/2 or -1/2. So that's why we draw electrons as arrows. The positive means it's +1/2. The negative means it's -1/2. If you saw an orbital that was nothing in it, that would mean it was empty. And if it has 2 electrons and they have opposite spins, it means it is full. Really, it refers to spinning clockwise or counterclockwise. And again, it doesn't matter which one you do first, as long as they are opposite. So electrons are only going to spin in 2 directions. So they're always going to be +1/2 or -1/2. The positive 1/2 corresponds to the up spin of the electron, and the negative 1/2 would correspond to the down spin of an electron. Okay, so our goals were to identify a quantum number, to fill in the Aufbau or quantum number orbital for an electron. So what might happen here? Okay, you might get an Aufbau diagram or an electron diagram that looks like this. And I might say, identify the quantum number of this particular electron. Okay, so remember my first number is N. It's my principal energy level. Here's 1, 2, 3, and 4. So my first number in my quantum number would be a 4. My second number refers to my suborbital. S is 0, P is 1, D is 2, F is 3. It's in a p orbital, so it's going to be a 4, 1. My next number is my m, or which of these 3 orbitals is it in? The middle one is 0. The one to the left is -1. The one to the right is +1. So I would have 4, 1, +1, and then my last number is either going to be +1/2 or -1/2. +1/2 is going to refer to the spin going up, and -1/2 is going to refer to the spin going down. This one is spinning up, so my answer or my quantum number for this particular electron would be 4, 1, +1, +1/2. Another example, what it would be my quantum number here. Take a moment in the video, see if you can figure out what the quantum number is all on your own before I tell you the answer. Here's my answer. It's in principal energy level 5. It's in 0, 1, 2, a d orbital. This electron is in the center, so m equals 0, and it's pointing down, so it's -1/2. That's how I would identify that electron's quantum number. We might also be asked to fill out an Aufbau diagram for an element, like oxygen. And when we do that, we need to remember Hund's rule, that we fill 1 electron up and then 1 electron down. Oxygen has 8 electrons, so when we look at those 8 electrons, here's how you should fill it. You should put 1 electron in the 1s orbital because that's the lowest. Then you should put the next electron there, also the lowest, and that orbital isn't full, but they have opposite spins. Then I filled 2s with an electron up and 2s with an electron down. And then when I go to fill my 2p, I still have 4 electrons left. But my first electron would go here, up, my second one up in a new suborbital, and my third one up in a new suborbital. Then I would double up because I have to double up, but I wouldn't double up before then. So my Aufbau diagram for oxygen.